Hocam sesiniz gelmiyor.
Teşekkür ederim. Okay. So last time we started studying surfaces. A subset of R3 is called the surface. What's the surface? I mean, what are the properties it has to satisfy? For each point of the surface, there should be some coordinate patch. Meaning that a function from D into R3 so that its image lies in R3 and actually it contains the point P. And we want this. X has to be 1-to-1 and its derivative from the tangent space of sigma, D into tangent space of, let's say, P here and Q here. So let me make this Q. Okay. No, this is R3. This map has to be 1-to-1 also. And of course, X is a smooth function. So it is infinitely many times differentiable. So we want both X and its derivative to be 1-to-1. So we have here in the UV plane some open subset, and X is a surface patch. So for any point here Q, there is some X and a point P like this, so that its image of D is something like this. Okay, and we want both X and its derivative maps to be 1-to-1. So this lies in R3. Okay, so that's the surface in R3. Last time we have seen that sphere is a surface. Now, we will do a couple more examples. Graphs of functions are surfaces. So let f be a function from R2 to R2, be a differentiable function. Then its graph. Sigma. So what is the graph of sigma? It consists of triples. Okay, UV and then f of UV. Okay, UV are in the plane, is a surface. R3 and X from R2 into R3. So this is my D, okay, given by X UV is just this triple UV f of UV provides a surface patch. At all points. Okay, so in this case, I may take my D to be the whole plane, okay? And our surface patch is just this function. So the graph of this surface could be something like this. For example, okay. Any point here, P, is the image of some point here. No, it's the other way around, Q and P. So X of P is equal to Q. So this is our surface. Okay. Well, we have to, of course, check the conditions that X is a surface patch, meaning that X has to be 1-to-1 and its derivative should be 1-to-1. Let's check that. We need to check that X is a surface patch. So first we have to check that X is 1-to-1. Let's see if it is. Well, it is clear from the description of X actually, right? So if X U1 V1 is equal to U2 V2, then of course, what is this? This is just U1 V1 F of U1 V1, and this is equal to U2 V2 F of U2 V2, but this already implies that U1 is equal to U2 and V1 is equal to V2. So the pairs U1 and U1 V1 is equal to U2 V2, right? So X is 1-to-1. What about its derivative? Oh, we had to also check that X is a proper map, right? I should so yeah, sure. F is a function and differentiable function. Yeah. And here we have to also show that this is a proper map, right? Proper map, meaning that X from D into its image is a homeomorphism. So we have to check also this condition. All right. So let's see whether what's the derivative of X. So derivative at any point, let's say P. Let's say P is just U comma V. What is this? This is just I look at the coordinates of X. So X is this X UV UV F of UV, and I have to take the Jacobian of this. Let's start with the first function. Derivatives of this with respect to U and V. Derivative of U with respect to U is 1. Derivative of U with respect to V is just 0. And then derivative of V with respect to u and v, so it is 0 and 1, and then derivative of f with respect to u and v, so it is f of u and f of v, right? And you see that this matrix has rank 2, right? So this is defined from the tangent space of R2, and it has values in the tangent space of R3. This is two-dimensional, and this has rank 2 at all points. Hence, dx is 1-to-1. Yes.
Hocam tahtayı biraz uzaklaştırabilir misiniz?
Oh, I hear. You mean this f? Or it doesn't have to be 1-to-1. F could be, for example, a constant function. Then your graph would be a plane, which is the surface. F doesn't have to be a 1-to-1 function. All we need is that f is a smooth function, so that I can take the derivative. Okay. Başka sorusu olan var mı? Bir deney göstereceğiz. Üçüncüsü, so the third condition is that x is a proper map. So it has to have an inverse, and the inverse should be also continuous. But you see, x inverse can be defined from the surface into D, is well defined by what? What is this? So if I have here u v, f of u v, what is the value of this? Well, it's just projection onto the first coordinates, right? Which is clearly 1-to-1, which is clearly continuous, which is clearly continuous. Right? And you see that x composition x inverse is the identity function of the surface, and x inverse composition x is the identity function of the D, which is, in our case, it is just R2. So x is 1-to-1 onto, it is continuous, and its inverse is continuous, right? So x is 1-to-1 onto its image sigma continuous with continuous inverse. Hence x is a surface patch. X is a proper map. And thus x is a surface patch. For all points, at all points. So x is a surface. So the conclusion is that this thing is a surface. So as your friend mentioned, we can use this to build many surfaces. For example, if you choose F, so okay, some explicit examples. For example, choose F to be just this function, F UV equals
Hocam
pardon.
kitapta kaldı. Evet.
Okay. Okay. All right, so let's choose this function, for example, this UV, and then let's say 2U plus 3V. So what is the image of this? So sigma, which is just UV, and then 2U plus 3V, right? UV is in R2. This is a surface. We just proved that, right? It's a surface. And what is this? This is actually the plane. The surface is nothing but the plane. Z equals 2x plus 3y, right? If you let this x and this y, this thing y and this thing z equals 2x plus 3y. Okay. In particular, you could choose this coordinate a constant, and then it would be a plane which is parallel to the xy plane. Okay, let's choose another one. All right, another one. So let me give this a name different than. So let's call this I and this double I. Let's choose F to be this gadget. So F UV is okay. 2 times cosine U. 3 times sine U, and then okay, 5, let's say. What is this? What is the image of this? What is the image of this? So if you call this X, this one Y, no, here I should, okay, I should do it like this. This is not correct. U here and V here, sorry. 2 cosine U, 3 sine U, and then V here. What is the image of this? You see, this is X over 2 squared plus Y over 3 squared equals 1. So it's an ellipse in the XY plane, and the Z coordinate is free. It means this is a cylinder with base and ellipse. So this is an elliptic cylinder. So, okay, it's like this. Okay, in the XY plane, yeah, yeah. Oh, okay. Yeah, this is not, sorry, this is not an example of that. Yeah, you're right. Yeah, this is another example. So this is not example of this thing. Sorry. So this should be example 4. I am sorry. Yeah. And I should call this. Oh, ya bunu tamamen yanlış yaptım ben. Sorry. Yeah, I don't know what was I thinking. Probably. Sorry. So this will be our next example, but yeah. Let me erase this. Let me do something. Okay. Cylinder is not a graph, of course. I could choose this function, R3. UV is just U squared minus V squared. So sigma, which is UV, and then F of UV in R2. So this thing is what? This is just the surface Z equals X squared minus Y squared. And it is something like this. Okay. Okay, it's a surface like this. Peki iyi olmadı. Let me redraw this. First, let me draw the surface and then locate the coordinate planes axis. Okay, so this is the z-axis. This is one of the axes, and this is the other one. So which one is which? In the xz plane, it's the parabola upward, and in the yz plane, it's also parabola, but it's downward. So this is the x direction. This is the y direction. Well, of course, this is not positively oriented plane, but anyway, it's not positively oriented, but it doesn't matter. Okay, so this is also a surface called saddle surface or saddle. Okay, let me give another example. So this one, so let this to be just, okay. Okay, A times cosine U, B times sine U, and V. UV are just real numbers. So this is a surface in R3, and this is just cylinder. So you see in the XY plane, this is just x over a squared plus y over b squared equals 1. So it's an ellipse. Here I take a and b to be positive numbers. This is an ellipse, and the z coordinate is free, so it's an ellipse like this. Okay, and the base of the ellipse is just sorry, this is a cylinder, and the base is an ellipse. Okay, now what's the surface patch at any point? At any point Q of the surface, we have a surface patch covering that point. I have a single surface patch actually. It is defined actually everywhere, but we have to be careful when we are taking specifying D. So X is given with the same formula at all points. So this is just A times cosine U, B times sine U, and then V, okay? All right. This function is, if you look at this way, this function is of course not one-to-one, right? Because sine and cosine are periodic with period 2 pi. So this function is not one-to-one. However, I can always, okay, suppose you want to write down a surface patch for a point like this, okay? What you can do, this point has some coordinate like this, right? So there is some UV here, which is mapped to this point, right? This point has coordinates U, V, and then, sorry, not UV, whatever, this coordinate, A times cosine U, something. Now, this function on the whole plane in R2 is not one-to-one. However, I can restrict my domain into an open ball here so that it is one-to-one. How can I do this? Well, if I choose U in an interval of length less than 2 pi, so if I choose, a maybe neighborhood like this, so meaning that I choose a surface patch like this. Okay, a small piece, then I would be okay. So how can I do this? Suppose this point has coordinates U0 and V0. So choose D to be what? I can do this. U0 minus pi, U0 plus pi. And then what about V coordinate? Actually, it can be anything, right? I can choose, okay, so it is this interval cross, maybe I can choose the whole R, meaning that I can choose the whole strip like this, okay? The whole strip. And in that case, of course, my surface patch will be something like this. Okay, it will go infinity in both directions, okay? And my point Q is here. So what we have to do, we have to check that this map X is one-to-one and its derivative is also one-to-one, and it's a homeomorphism. Yeah. It is not this much. It is the whole cylinder except a line, actually. Just the line opposite to this point. So, right? So, yeah, you have this line back there. You just cut it, cut through along that line, and then you have the surface patch. You could, of course, choose something like this, pi over 2, pi over 2. Then it would be something narrow, okay? Let's see that this function is one-to-one. Okay. So X defined from this interval, let's say, cross R into R3, right? XUV is just A times cosine U, A times sine U, and then V. So this function is one-to-one. Why is that? Well, if x u1 v1 is equal to x u2 v2, then of course I have cosine u1 is equal to cosine u2, and sine u1 equals sine u2. But this means what? Cosine, and I am on this interval, right? U0 plus minus pi over 2. Well, this implies, right, u1 is equal to u2. You are using both of them, of course. Okay. And of course, this also implies v1 is equal to v2, right? Because the last coordinate is v. So this means if this is one-to-one, what about its derivative? Dx. So at any point, what are the what is the Jacobian? So I have to take derivatives of these functions. Derivative of a times cosine u. So minus a times sine u. And then derivative with respect to v is just 0. And then, okay, this function derivative with respect to u. So it is a times cosine u, and then 0, and then derivative of v with respect to u and v. So it is this function. You see, both of these numbers cannot be simultaneously 0, right? So either this one is non-negative, non-zero, or this one is non-zero, because, you know, if you square this 2, you get a squared. So minus a times sine u squared, a times cosine u squared is just a squared, and a is positive, right? That's how we choose a and b. Here. So this means hence either a times sine u or a times cosine u are non-zero. It's non-zero. This means hence thus dx at p has rank 2, so that dx is 1-to-1. Okay. Well, to prove that it's a proper map, we have to exhibit inverse for it. Okay. So x inverse from the surface patch from the image of D into D is given by x inverse. A typical point is this: a times cosine u, b times sine u, no, again a, and then V. Bunu yanlış mı yaptım? A, B'di değil mi? Niye? This was B. I'm sorry. Okay. So I divide this by A, this one by B, and then we get 1 here. Okay. All right, so what would be the image of this? Image would be just UV. Okay. This map is well defined on the image XD because our function is 1-to-1. Okay, X is 1-to-1. So UV is mapped to here. So this point is mapped to here. Okay, it's chosen to be 1-to-1. You may wonder whether this is differentiable, right? Well, actually, I don't need that. But yeah, we need to show that it's a continuous map. Is this continuous? Well, X inverse is continuous. Continuous since it is the restriction of which function? This function. Let's say H from R3 into R given by R2, sorry, given by what? Okay. Şöyle yapabiliriz aslında. Okay. Şu koordinata X dersek bu Y, bu Z. H, X, Y, Z. This coordinate will be just Z. What about this coordinate? Well, you see, one of them is non-zero, right? Yeah, maybe I could have chosen but that's not the inverse. We can do something like this. Either X or Y is non-zero. So suppose X is not zero, then maybe I need to choose our interval even smaller. You see, Y over X is just B over A tangent U, right? So to get u, I need to do what? Ay over bx tangent u, and u is just tangent inverse ay over bx. So, and here I can write ay. Okay. Tangent inverse ay over bx, and then z. This function is continuous, okay? Yeah. So what we should do, at the points x is not 0, I define it this way. At the points y is not 0, I define what? If y is not 0, then x over y is just a over b cotangent u, right? So in that case, the formula would be u is just cotangent inverse bx over ay. Okay, so this function is piecewise defined. And these are equal to each other, right? Although the expressions are different, they are equal to each other, right? At the points where x and y are both non-zero. So this means h is differentiable, therefore continuous. Well, h is continuous, therefore x inverse is continuous. H is continuous, and hence x inverse is continuous. Therefore, it's a proper map, okay? It's a proper map. Okay. Oh. So, here is a theorem which provides more examples. Let G from R3 to R be a differentiable function. And C is a real number. Real number. Set M to be the inverse image of G, C under the function G. So what is this? This is the point set of points in R3, so that G, X, Y, Z is equal to C. Okay. Assume further that the differential dg is not 0 at any point of M. Then M is the surface. All right. And let's talk about the proof of this in the next hour. So let me stop now for a break.